What's the status of the Jupyter Notebook story? Do you have it working?
All are downloading on the single server, so it's taking time.
Okay, so you don't have it right now?
No.
Okay. We will, what I'll do is then I'll go back to the slides. We will, and at least I'll walk you through the examples, and in the afternoon we can go back when you have it.
Yeah.
Oh. All right. So what I want to do now is walk you through the expectation maximization for the coin toss example. Remember the coin toss example? We are trying to figure out two things. We've got two coins. I want to find out what is the probability of heads for each coin, and also understand from that what is the actually there is an error there which we'll fix in a moment, and also try to understand what was the assignment for the coin for each particular toss. Okay. Remember in EM algorithm, what are we trying to do? We'll create the complete log likelihood. We're going to take a complete log likelihood, which is as if I knew the data. I'm going to take the expectation of that and then use that to compute the next parameter. So what I want to do is, in order to compute that expectation of the complete log likelihood, I want to look at the posterior distribution that a coin given the observation and theta k. So this, I'm just defining it easily, just to keep track of things, as P of y given x. So the conditional distribution of y given x and theta, this is proportional to the joint distribution, probability of y and x given theta. I can rewrite it in a different way. So remove this in your slides if you have it. This is an error. This is simply P of y given theta k, the probability of x, and given y and theta k. There is no equals a there in the notes. This we know, the first part is just a probability a half. The second part is a binomial distribution, theta ky, and the k part comes from the fact that these parameters is the kth iterate to the power x, 1 minus theta ky to the power m minus x. This is what the log likelihood is. So let's call this number Ly of x. The probability is nothing of a given x is nothing but the log La of x divided by La of x plus Lb of x. This is some quantities that I'll need for my Python code, and that's why I'm putting it over there. The complete log likelihood is xi log theta yi. Xi is the result of the coin toss, theta yi is the corresponding coin. We don't know what theta yi is, so I'm going to take the expectation of this. There is a second part which is m minus xi log 1 minus theta yi. This is nothing, this is the heads, these are the tails. These are yi's are the labels for the coins. We don't know what the coins are. But next step, I'm going to, using these probabilities, I will be able to compute the expectation of this. So using PAX and PBX, we get that the expectation of log theta yi is PAXI. This is the probability given xi that the coin was coin A, log theta A. PBXI, which is the probability given xi that the coin was B, times log theta B. The expectation of log of 1 minus theta I is similarly PAXI log 1 minus theta A, PBXI log 1 minus theta B. This is exactly what the log likelihoods are. Q theta theta k is take the complete log likelihood and take the expectation of that with respect to x and theta k. So what do we have over here? Let's go back. This is what the complete log likelihood is. So xi times log theta I plus m minus xi times log 1 minus theta I. So I'll take the expectation of this, I'll take the expectation of that. These are just constants. I know the expectation for those two quantities are up here. So if you put all of them together, you get this expression. Xi times PAXI log theta A, which is all the contributions that are coming from here. Xi PBXI log theta B, which is the contribution that's coming from there. PAXI times m minus xi 1 minus theta A, which is coming from there. And m minus xi PBXI 1 minus theta B, that is a contribution coming from there. There are four contributions from here. They're all sitting over here. Now, if I want to generate the next estimate, I want to estimate the next value of theta A, I want to estimate the next value of theta B. So it splits up into two different optimization problems, one involving this expression and one involving that expression. So theta K plus 1 is nothing but the maximization of the expression involving either theta A or theta B. Right? So it splits up into two optimization problems, one for theta A and one for theta B. Now think about if you knew exactly what each coin was, which was the particular coin, how would have this expression look like? Just to put a sanity check so that we know what is going on. Suppose for each particular coin xi, I knew exactly what yi is going to be. I knew exactly whether it was coin A or coin B. What would this expression look like for that particular case? What would be happening in that case? What would be the difference between the expression that I've written here and the expression where I don't know? This is the expression when I don't know what was the coin chosen. But suppose I tell you in every coin toss which was the coin chosen, what will be the difference in this expression? What will happen? What should change? Sorry?
P of xi can be taken out, right?
Not taken out. P of xi will change. It will change to what?
That will be known.
Sorry? P of xi will, what will happen to that?
That will be known if I know which one.
It's known. So in terms of, if I want to say that in terms of probability, what does it mean? It will be deterministic. It will be either 0 or 1. So this PA of xi, in the case where I know the coins, will either be 0 or 1. Either for the ith trial, the coin chosen was A, in which case this just becomes 1. If for the ith toss, the coin chosen was not A, this will become 0. And similarly, this will become 1. So there will be a switch going on here which depends on which coin was chosen. Similarly over here, if coin A was chosen, this will be 1, and if coin B was chosen, that will be 1. So if you look at this summation, what will happen? This summation will just be summation over all xi's for which the coin was A. This will be summation over all xi's for which the coin was B. And so then if I want to optimize this, as you guys had already figured out, theta, the optimum value of theta A will simply be take the sum of all coins for which the coin was A and divided by the total number of times the coin A was chosen. Here, take the sum of the xi's for which the coin was B and take the divided by the total number of times that coin was chosen. Instead, now what we are doing in the EM algorithm, we are saying I don't know which coin it was, but I'm going to put a weighted combination here, weighted by the probability that the coin was A. Over here, I will write the weighted combination assuming that the coin was B. That's all that has happened in some ways. That's only thing that we have done after all of those mathematics is to put this weighted combination. But now we are at a point where we can justify this based on some assumptions that we have made about the log likelihoods in terms of what is going to happen. But the optimization problem, once we have this, becomes very simple. Great. Now I have this optimization problem. Here we know intuitively that the right thing to do is take this, divide by the summation of that and this, and you'll get the answer. That's basically what the optimal solution is. But in order to justify that, why that is the optimal solution, one possibility is to take the derivative and set it equal to 0 and check that it works out. There's another possibility which I want to introduce because it becomes much easier to think in terms of what's going on. And for that, I'm going to introduce this optimization problem which looks odd, but I will connect it back to the story that we want. So suppose you have an optimization problem of this sort. You maximize over a probability mass function q. So the sum of the qi's is equal to 1 and all the q's are greater than or equal to 0. So I'm maximizing over a probability mass function of summation of I going from 1 through I, ci log qi, and I also have this condition that all the coefficient ci's are greater than or equal to 0. Why am I interested in that? Because the problem that I'm trying to solve is this. I want to maximize over theta, summation over I, xi, pa, xi, log theta, plus summation over m minus xi, what is it, PAXI log 1 minus theta. This is the same thing as saying maximize over theta 1 plus theta 2 greater than equal to 1, theta I greater than equal to 0, and over in this case I'm going to write the summation over I xi PAXI log theta 1 plus the summation over I xi, not xi, m minus xi PAXI log theta 2. This is exactly the same thing. Here I use the fact that if theta 1 plus theta 2 is equal to 1, if this is log theta 1, that should be log 1 minus theta 1. Here I've just written the optimization problem in using two different parameters. Each of the theta 1 and theta 2 is greater than equal to 0, I going from 1 and 2. Sum of theta 1 and theta 2 is equal to 1, and I want to maximize this quantity. This guy, call it C1. This guy, call it C2. I know that C1 is greater than equal to 0, and I know that C2 is greater than equal to 0. Because this is some probability times xi's, which are coin tosses, which are greater than equal to 0. This is m minus xi, I have tossed the coin m times, so m minus xi is positive, times some other probability which is positive. So both this C1 is greater than 0, C2 is greater than 0. So it looks like that. Each of the c's are greater than 0, log qi's, the sum of the q, to make it look identical to that, let's change this, call this q1 plus q2 equals 1, q1 and q2 greater than equal to 0, q1, q2. It's exactly the same thing, and this is why I'm interested in that optimization problem. Now, if I'm interested in that optimization problem and I have any time a non-negative plus log qi, I should think in terms of a Kullback-Leibler distance, and this is what I'm going to do. The CI's are greater than equal to 0, so I'm going to normalize them by their sum, and I get a probability mass function now, right? PI is nothing but CI divided by the sum of the CK's. Well, you might object, what if the sum of the CK's is equal to 0? Do I worry about it? No, then I don't have an optimization problem to solve. If all the C's are equal to 0, I'm done. So at least one of them has to be non-zero, and if one of them is non-zero, this probability distribution is well defined. I'll do that. Then this maximization over Q of this quantity Ci log Qi is the same as I multiply, divide by the sum, maximum over Q Pi log Qi. And what I've done is multiplied and divided by the summation. I'm just labeling, my labels are all off, but it's basically, think of n and m being the same. So this is just the summation. I multiplied and divided, so I take the summation out. So if I want to maximize this, I can multiply and divide by Qi by Pi. I get Pi log Pi minus Pi log Pi over Qi. What did I do over in this process? Inside the bracket, I multiplied and divided by Qi. So Qi over Pi times Pi. The Pi term, I took it over here. There was another term which is Qi over Pi. I took a negative sign over there and made it Pi over Qi. That's what I did. Why am I going through all these gymnastics? Because this guy over here now looks like Kullback-Leibler. So I want this Kullback-Leibler sitting over here, and then I'm in business. So if I write the summation out, this guy doesn't depend on Q, so it comes out. This maximization over Q of a negative sign becomes minus the minimum of the KL divergence between P and Q. But if I'm minimizing the KL divergence, the optimum value of Q that I choose is actually Q star equals P. Okay, so this is the minimum distance that is going to happen. The optimal Q star turns out to be Q star equals P, and then I'm done. Okay. All right. So now if I go back to this story, actually maybe the slides are up there as well. So for the coin toss example, you have this theta A, theta B. So now I have a form, this is my C1, this is my C2. This is my q1, that is my q2, and theta y turns out to be take the value of c1 divided by the summation of c1 and c2, which is exactly that. So it will be the summation of I going from 1 through n xi p y xi divided by m times the summation of the weights. Now if you compare this expression to what we had before when we knew the coin, this part here will be always 0 or 1. So the numerator is going to be the summation of all those values of xi for which the coin was A, for example, divided by the number of times the coin A was tossed, and equivalently coin B. So all that has happened right now is that we have changed the weights. Okay? So nice interpretation, assign xi to y is equal to y with that weight, and then you interpret, you keep on going from there. So I'm going to go through this other exercise in a moment, but what I want to do now is go to the Python notebook and show you what's happening there so that you can get an idea for it, and then in the afternoon we can go back to it again and see what's going on there. So for those of you who are, does anybody have a Python notebook working? Still downloading? Yes. Working, perfect, good. So at least some of you have it working, so over lunch maybe those who have it working can help those who are still downloading it. So you can get to see what's going on. First of it is all a bunch of, in fact some of those things I don't actually need for this. I just took it for various things. All I'm doing right up there is basically importing a lot of Python libraries which are necessary for doing various kinds of things. First 3 of them have just operating system like stories. This one is a library that is used for plotting. And the difference later on, as I show you various things, I'll show you what to do. There is a command for inline plotting. You don't have to, these things, this plot, matplotlib, inline, and plot style use ggplot. This is basically a kind of a style of plotting. Don't worry too much about it. NumPy is a routine which is a library which has a lot of numerical routines. We'll be able to use that. Pandas does, they give you data frames, so I don't think we'll use it today as much, but if I'll see whether there's down there something is happening or not. What else can I tell you? Yes, the other thing is, as you're going to be writing various things, I'll give you one assignment problem right away, which is not there, but I'll assign it to you in a moment of what to do. So this np random dot seed, what I'm trying to do here is I'm generating data randomly, so I'm going to assign a seed. As a discipline, you should always, whenever you're doing anything random, particularly when it comes down to data analysis and things like that, always set the seed. Can anybody tell me what the advantage of this seed is? It reproduces everything, perfect. So you should never forget to set a seed. There have been situations where my PhD students at some point have come very excited about showing me a result that they thought was absolutely great, but you cannot reproduce it because they didn't know what the seed was. And trying to infer the seed from the data is nearly impossible. And so set the seed. We will actually import some optimization routines from SciPy, which is a bunch of scientific routines. We'll import minimize. We will also import Bernoulli and binomial. These are 2 distributions that I need for later on. Yes?
Like while assigning the seed, it may possible that it may move to a solution which is not a good solution.
That's fine. Because the point of this exercise is that I am trying to get reproducibility. So in the real case, when I have real data, I don't have to worry about this.
In real data sense, like I'm doing something, some exercise, I've given the seed.
Yep.
I'm able to reproduce, that's good, but the solution is, I'm assuming for the first time, it is not a good.
Yes, but what I would do is I will have lots of different samples. So I don't want to rely on the machine's randomness. I would rather generate the samples myself, so know what is going on. Because if I rely on the machine's randomness, it's going to be tough. Another trick that you can play is sometimes you can run it off of the CPU time. So you can write a seed which is defined as a CPU time and then record the seed somewhere so that you know that if you got a very good result for that seed, what is going to happen. That's another trick that you can play. Okay. All right, so this is the this is the coin toss example. It's just written there, the exact same thing that we talked about. Experiment with coin A, which has probability theta A of heads, coin B that has probability theta B. We draw m samples as follows. For each sample, we pick one of the coins at random, specifically with half-half probability, flip it m times, record the number of heads and tails that sum not to n but to m. Here. Actually, let me run this to make sure that it is running here. Good, perfect. Good. To m, if we recorded which coin we had used for the sample, we have complete information and can estimate theta A and theta B in a closed form. To be very explicit, suppose I drew m equal to 5 samples with the number of heads and tails represented by the vector x. The sequence of coin tosses being A, B, B, meaning first time I chose coin A, then B, then A, then B. Then the complete log likelihood looks like that. Probability of x1 given theta A, x2 given theta A, x3 given theta B because the coin was B, x4 given theta A and x5 given theta B. Where P of x given theta is a binomial probability mass function with m trials and probability of success. Where did it go? We will use yi to indicate the label of the ith coin. That is, we used coin A or B to generate the ith sample. We'll come back to this function in a moment. I don't need it right away. Let me just define it and we'll go further. That's good. So here what I've done is I chose m equals 10. So I'm doing 10 coin tosses. The real value of theta A is 0.8. The real value of theta B is 0.3. Theta 0, this is simply an estimate. This is the real value of theta, which is theta A and theta B. Coin A is Bernoulli theta A. So if I call a coin A, what I've done here is I've defined a function. In Python, if I look at what coin A is, for those of you who are going to play with this later on, I'll force you to play with it. So it basically, it's coin A is no longer, it's not a variable, it is actually a function. It's a SciPy statistics distribution random variable frozen. What does frozen mean? I have taken some parameter theta A and froze it. So it's set equal to Bernoulli 0.8 and this coin B is set as Bernoulli coin 0.3. Okay, what happens over here? This is also a bit of both Python and data analytics going at the same time. So let me unpack this story. Let's look at what is going on at the bottom inside over here. Let me actually make this. Okay, so now it's better. So remember, y tells you which coin it is. So it's coin A, B, A, B, A, B. That's what these coins are. 0 stands for coin A, 1 stands for coin B. So you have A, B, A, B. Correspondingly over here, I'm generating random variables. I am generating coin A random variables. I'm choosing m of them. So Bernoulli's, remember? Bernoulli was basically a 0, 1 random variable with parameter theta A. So what I've done here is I've generated m coin tosses using coin A. Again, m coin tosses using coin A, m coin tosses using coin B, m tosses A, m tosses B. That's what I've done in this calculation. So if I want to generate binomials, what do I have to do from these coin tosses? If I want to generate binomials, what do I do over here? What do I do with these coin tosses if they are Bernoullis? How do I get a binomial? Add them up, right? That's what this function says. It says take the function sum, and this mapping basically says that take this sum and map it to all of these quantities. So all it's, when you look at fxs, all it's doing is that it's mapping this summation to all of them. It will sum this and that and that and that and that. So if I look at what that looks like over here, it's a mapping. It's just a mapping from one to the other. If I make it into a list, it gives me the numbers. So coin A came out to be 7, coin B came out to be 9, coin 3 turned out to be, this particular thing turned out to be 2, that came out to be 6, and that came out to be 0. Now looking at this, does it seem about consistent with theta A to be 0.8 and theta B to be 0.3? Seems about reasonable. The first, the second, and the fourth components are large, or in Python lingo, 0, 1, and 3 are large, and 2 and 4 are small because the corresponding theta was 0.3. All right, good. Y's are these quantities over here. Index of A is basically looking at, for those values for ysk was equal to 0, meaning these are indices for coin A, these were the indices for coin B. That's basically what the calculation there are. Okay, just to show you what happened over there. Ind A is 0, 1, and 3. So in Python starts counting from 0, it says 0, 1, and 3, and in B will be 2 and 4. Okay. All right. So let's get rid of this cell, we don't need it anymore. Over here, what have I done? I have converted my mapping into an array. So X's is an array, numpy array of the number of coin tosses. The maximum likelihood estimate of A is basically take the summation of X over the index A divided by M times the size of index A. This is what happens to the maximum likelihood estimate of A. What happens to the maximum likelihood estimate of B? Take the sum of X's for all those elements that belong to index B, divide by M times the size of index B. So you end up getting that. Print M1A and M1B, and if you run this, turns out to be what happened over here. Okay, turned out to be 0.8 and 0.2. That was the estimates that we ended up getting. So what was the value that we started from? 0.8 and 0.3. So the first one was estimated correctly. The second one was not estimated correctly because we had 2 samples, we had 3 samples. Maybe if we had more samples for coin B, we would have been a little bit better estimate. There is no guarantee, by the way, that the maximum likelihood estimate is the true value. The maximum likelihood estimate will converge to the true value as the number of observations grows. We have only 5 observations, 3 of them for one of the coins, 2 of them for the other coin. Very few, there is no reason to believe it will converge. Okay. Now, instead of, this is a formula that I know. Instead of that, I can write this as a function and optimize, and this is where I will give you your first homework problem that you need to do, and hopefully your friends who know Python can help each other out. So what I've defined here, let me unpack this function for you. So I've defined something called the negative likelihood. Why do I define the negative likelihood? Because SciPy, the optimization function that I'm going to use, like to minimize things. We like to maximize things, it wants to minimize things. So instead of trying to do that, I took the negative word. What happened over here? Let's unpack that story. It says, given the thetas, which is theta A and theta B, n, which is the number of coin tosses, the x's and the y's, you return np.sum. np.sum is basically numpy sum, and this np dot just stands for the fact that I've imported numpy as np, so every time I want to use a function I have to call it np dot something else. So it's summing. What is it summing? Binomial distribution with n coin tosses. Where is my story over here? Yeah, n coin tosses, theta corresponding to that y times log PMF evaluated at the point x. And we will just now I'm going to write this on the board so that we know exactly what is going on, because I'm going to ask you to modify this. For xy in this quantity called zip xsys. So let's unpack all of this so that you understand what's going on. That's that password, so I'll leave it over there. Okay, so first thing is, what does this zip do? So my xs or x's stand for whatever it was, 7, 9, 3, 6, 0, something like this. Y was 0, 0, 1, 0, 1. When you do a zip in Python, it basically creates pairs. 70, 90, 31, 60, and 01. So the zip command, when I said zip xs, ys, that's what it will create.
It will create 25 pairs.
No. It does pairwise. It's not, it doesn't create, zip only creates pairs.
Randomly.
Not randomly, correspondingly.
Okay.
So zip doesn't create an array, it only creates corresponding values for what is going to happen. So whatever is the corresponding number, it will pick that. Okay, and then what is going on over there? So the next one, it says take x and y belonging to the zip. So it will sequentially go through this, then that, then that, then that, then that. That's what this for is going to do. For x, y in zip, it will take first value to be x, so it will take that to be x, the next one to be y. It is a loop. For will always give me a loop. And then it will, this square brackets at the two ends of it basically says to me that create a list of all of these quantities as you're going. So the list will be, look at the log of the PMF of the binomial distribution of n theta y evaluated at the point x. That was all of this second statement says. Binomial distribution n at theta corresponding to y, take the log of the probability mass function of that particular distribution evaluated at the point x. So it will do, first it will do y1 x1, next element will be log PMF binomial n theta y2 x2 da, 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 da. In our case, how many do we have? 5. And let me put that in Python notation. Everybody with me so far? All it's doing is that it created this list and now it's created a list of these things. The function sum, np.sum, will just add all of them up with and put a negative sign in front of it. So the sum will just say sum all of this and put a negative sign behind it. Okay? Now, just so that we have in mind what is this going on here, we are going to create the negative likelihood when we know the values of the y's. What I want you to do as your first assignment is what happens when you don't know the value of y. You have to change this function. How would that function change? What will be the expression? How would that function change? So for any one of these, the corresponding function that you need to write, which we can work with later on once you've gotten your Python working, is over here. I have to put log binomial n theta 0 evaluated at the point x, generic x, plus PMF binomial, but this times I have to put the PMF outside, so n theta 1 x, and then take the log and then take the sum. So you don't do the zip anymore because you don't know the y's. These are gone, you don't know them, so you'll have both theta 0 and theta 1. So instead of thetas given the value of y, you need both of them, and it'll be interesting to see how you want to do that, and we will figure out a way of figuring that out. But right now I'm assuming the case where you do know the values of y, and I want to optimize that, not using this answer that I know, but by calling a particular minimize command from from SciPy. I just want to use how to do this in optimization in SciPy. So what's going on over there? I have the negative, where is my pointer over there? Good. I have my negative likelihood function. This takes as input theta 0 and theta 1. So I'm starting both theta 0 and theta 1 at 0.5 from 50% point. It takes other arguments. That function takes the first value as theta, right there, and then it has three other arguments, n, x, and y. That's what this is saying, arguments m, x, and y. M is the number of coin tosses, x's are the results of the coin tosses, y's are the coins that I use for each of those coin tosses. I give it bounds, so I want each of these thetas to be between 0 and 1 because they are probabilities, so that's what it sits there. This is I forget what TNC stands for, truncated Newton something. So it's just basically a method that I want to use for optimization. I'm putting the maximum, an option that the maximum number of iterations is 100. And then I do a little prayer and you get the answer. And it's not very surprisingly 0.8 and 0.2. If this optimization works, it should give me exactly that because I know that that's the optimal solution. It converged there. Why did I want to tell you about this thing? Remember at the beginning of this lecture, I was telling you that as far as I'm concerned, pretty much everything is there in Python. I don't have to show you what to do in optimization because you can just call the function. It gives you the answer. The only places where you have to worry about is what I have to tell you is whether certain things will, how to use them as various places. So what I want to do as a first exercise for you, which I'll assign, is how do I now do the case where by changing that function. I want to be able to change that function in order to get the situation where the y's are not known. What I'm going to do is show you what happens, the expectation maximization story. Whatever the codes that we generated, we want to use it over here. Okay, I expand the x's to include the number of zeros. Remember, let me actually write out the expression for you so that you can keep track of what's going on in the code. So remember what we were trying to do in the maximum likelihood story. I have the summation of I going from 1 through n xi, pa xi, the whole thing multiplied by log theta a, plus the summation of I going from 1 through n, capital N rather, m minus xi, pa xi, whole thing multiplied by log theta, log of 1 minus theta a. And then I have the same expression here for log theta b, log 1 minus theta b. Same exact thing, except that in this expression you'll have pb here and pb there. Otherwise everything exactly the same. This is what our expression was. And since I'm going to use both need xi and the number of zeros, I have just created a new one which I called extended x or x extended, which keeps track of both the zeros and ones. Right? It just computes vectors or combinations. For thetas, theta a 1 minus theta a, theta b 1 minus theta b, I put the initial estimates to be 0.5 and 0.75. Once we run it, there was a comment made during the break about what to where if I initialize the theta differently, what is going to happen. So we'll play around with that in a moment. There was another comment that was being made about what to do with here. So if I want to randomly start from here, what would I do? How would I randomly initialize things? There's a function called np.random.rand which generates a number between 0 and 1. Pick that to be some number between 0 and 1. That will start off the thing. Here I'm just taking it to be 0.5, 0.5, 0.25, 0.75. I'm putting a tolerance which I'll use later, which is my convergence tolerance. If things don't move by 0.01, I'm just going to stop. If my log likelihood doesn't improve by the amount of tolerance, I'm going to stop. The number of iterations that I'm choosing are 500. I'm starting from a log likelihood value to be 0, and I'm going to compute from there. Okay. VS, okay. What's going on over here? This is exactly the stuff that we have in the notes. So I'm trying to compute the new log likelihood. In order to compute the new log likelihood, which is this expression, I need to compute the probability of A given xi and the probability of B given xi. So I look at the log likelihood. This is basically looking at x times np log theta 0. So what's going on here is I'm looking at each of those quantities. So now remember, I have xi and 1 minus xi, or not 1 minus m minus xi. This is sitting there. And then I have theta and 1 minus theta. So I take the log of that. So it goes and it operates it along the way. So now this becomes xi m minus xi, and this becomes log theta comma 1 minus log theta. Oh, sorry, log of 1 minus theta. That's what this expression does. So it's going to multiply it component wise. So it's going to multiply xi with log theta, m minus xi to log 1 minus theta, and then the sum outside is taking the sum of them. So this is basically computing the log likelihood for coin 0. That's computing the log likelihood for coin 1. The denominator is the summation of them, and PA is nothing but the exponent of this log likelihood divided by the denominator. PB is nothing but the exponent of that log likelihood divided by the denominator. You can go and parse it yourself to make sure that these actually work. Now I'm computing the theta. I'm going to take the inner product of PA and X, inner product of PB and X. That tells me, which is basically doing this quantity. I'm taking the inner product of X with its corresponding PA, the other component of X and its corresponding PA. That's what is happening here. In VB, I'm doing the corresponding calculations that I have to do over here. I complete the log likelihood by PA times the log likelihood of A plus PB times the log likelihood of B. I compute all of them. This is the M step, which is the new value of theta. Update the values of parameters given current distribution, which is the summation of this Vs of A times divided by the summation. That one is basically what it's doing is that it's taking this component, dividing it by the sum of these two, taking that component, dividing by the sum of these two. That turns out the new values of theta. That's it. Okay. A lot of things went by, but I'm hoping that you have a lunch break where you can just take a look at this and see where we are, and then if you have questions, feel free to ask me what's going on. So if you run this, no, I was way up there somewhere. Oh, XX is not defined, so I should need to run this one. Yes, good. And basically now we converge to 0.79 and 0.2. That is the estimate when you do not know the thetas. So remember now what happened over here is I've compared this here as the estimate that I knew the theta and I converged to 0.8 and 0.2. Here I'm doing the EM method. So in this calculation I actually don't know what the coins were, but I still converged to the right values of theta A, or close enough to the values that the maximum likelihood estimator would have converged. So let's play around and see what we can do here. So what's the worst distribution that I could give it here?
0, 1.
Well, 0, 1 is terrible. Let's not make it that bad, because 0, 1 there is a problem. You don't even allow for the possibility of seeing the other coin. So but if I have two coins that I'm trying to differentiate, what do I want to do? If I were to give this to be sort of 0.1, 0.9 for the first one and 0.9, 0.1 for the second one, is that a good distribution or a bad distribution? Am I making my life easier or harder? So when I have two coins and I want to differentiate them, what is the worst possible thing I could start off with? Both 0.5, 0.5, right? Because then I am giving the initial guess has no information whatsoever. So let's try that and see what happens. Surprising? It just got stuck. Could not do anything. Everything is symmetrical. There is no, you did not differentiate it at all. And if you don't differentiate it at all, it doesn't do anything. So I can reduce my tolerance a little bit and make it 0.01. Still it doesn't make any difference. It just gets stuck. There's nothing it can do. So if I go back and change that thing to be a little bit, give it a little bit more movement, maybe make it 4, 5, 5, 5, or maybe make it, let's try be a little bit more ambitious and see what happens then. So now I've made a little bit asymmetry between the two, and maybe it will recover. It converged, and now it's going to 0.79, 0.22. Not bad. So in one of these things that if you have a situation where everything after the fact is symmetrical. So what happened here was that once I tell you to give you the coin, and after that everything is the same. So if you start off from a situation where the two coins look identical, there is nothing in this algorithm which is able to recover from it. Because remember, how does this engine work? It tries to compute the chance or the probabilities of the coin given the posterior distribution. You started it to be identical. So the probability that they were going to be coin A or coin B will be exactly the same. So the new estimate will be exactly the same. Come back, they will be exactly, you will predict again that the probability of seeing the two coins are exactly the same, and you'll keep on going. As a result, there is no information. You give it a little bit of asymmetry, it picks up the difference. Okay, over here all we are doing is calculating this quantity. I've defined a function. All it's doing is exactly the same thing that was done over there, except that now we are sitting with a function where I can give it the number of iterations, I can give it the tolerance, and it'll compute the answer. I didn't call the function. So if I call the function somewhere, let's call the function here. What was I working with? What did I call the beginning theta here? Theta, not theta s. There's some shape issues. Well, let's not worry about it. We'll fix it later. It's a question of putting the thetas, assuming it's in particular directions. We will fix it later. Okay. The next thing that I want to do is go show you another simple example where I'll have to do the calculation a little bit by myself. So for that, I will go back to the notes now and show you another very simple example so that you get an understanding of how this EM works. Let's go back to this view. Where is it? Full screen mode. Good. So we played around with this. For this one, if I started off with a little bit of a difference, we'll end up getting something reasonable. Here's another example that will motivate things to see what we can do with these. All right. So let's assume that I have a random variable x which has 4 components, x1, x2, x3, x4, and it is a sample from a multinomial distribution with some n being the number of samples that I draw. Pi theta is the probability for each of those 4 components, and pi theta is given by this vector: 1/2 plus 1/4 theta, 1/4 minus theta, 1/4 times 1 minus theta, and 1/4 times theta. So here if I look at this quantity, how can I, what is, and if I want to write out the expression for this, you will end up getting the log likelihood for this quantity and the reason I want to write it out is because I want to ask you to see how we can split this. So the log likelihood would be x0 or x1 log of plus 1/4 theta plus x2 log of 1/4 1 minus theta plus x3 log of 1/4 1 minus theta plus x4 log of 1/4 theta. Right? This is what the quantity is going to be, and I want to maximize this with respect to theta. That's the optimization problem that I want to solve. Okay? Which of these four terms is going to give me trouble? Which of these four terms in the log I don't like? If you want to think about trying to maximize this quantity with respect to theta, if one of those terms were not there, life would have been very easy. First one. Why do you think it's the first one which is good or which is bad? Sorry? Yeah. There's a summation inside the log, but there seems to be something over here too, right? Does it bother me? No, because these are multiplications. So this x, remember x is data that's already given to me. So this 1/4, log of 1/4 will just separate out. So this log of 1/4, I might as well just forget about it. These will not affect the optimization problem at all, because this will just be x2 times log of 1/4 outside, x3 times log of 1/4 outside, x4 times log of 1/4 outside. So it doesn't matter. So it will be 1 minus theta, 1 minus theta, theta. Lovely. This is a problem, because this I cannot split. So if I want to think of this as a missing data problem, how would I think about it? I don't like this. This is a trivial example again. I don't like this inside. So how do I think about splitting it? Remember, every time I want to split something, it's as if there was something missing that made me sum the probabilities. I did not know what the underlying quantity was, and that's why I got sum of probabilities. So how do I think of this as a missing data problem? That somebody gave me something, and if I give that information, life is great. Yeah?
Can you rearrange the first term like 1/4 into 2 plus theta? That can be similar like other three terms.
2 plus theta again it's the same thing. So I love theta and I love 1 minus theta, because those are the two things that I can do something with, because theta becomes a probability, 1 minus theta becomes the other probability, that's fine. 2 plus theta, it's almost as bad as 1/2 plus 1/4 theta. But 2 plus theta still doesn't solve my problem, because all you did was added it in a different way. I want to get it out of the log. So if I want to make it as if they gave me the missing information, life would have been easy. So in this EM algorithm, many a time what you have to do is postulate what might be the missing data. How do I structure it as a missing data problem? Any ideas of how I could think about this as missing data? Pretend as if you had some more information, and that information was taken away from you, and that's why you got this. Okay, so let me go forward. So this is what the log likelihood would look like. This is exactly the story that we did. This is what I've written down. But let's go. I could directly optimize this, and in the in the code I will show you how to directly optimize this, and then we will see what happens to that and compare it. Instead, I'm going to assume that suppose there was actually a 5-dimensional data, y1, y2, y3, y4, y5, which was multinomial according to that distribution. How did I dream up that distribution? I don't like these two probabilities, so I just took them as separate. I don't like the fact that they added up, so I just took them as separate. So 1/2, 1/4 theta, everything else the same. And so now what happened, what was the missing part here? So when I look at x, somebody forgot to give me y1 and y2 separately. They gave me the sum of y1 and y2. They gave me y3, y4, y5, all right. So the probability distribution for y3, y4, y5 exactly 1/4 1 minus theta, 1/4 1 minus theta, 1/4 theta. But what about the distribution of the last guy? It's the summation of these two. It's 1/4 plus 1/4 theta. So that became y1 plus y2 turned out to be the answer. So the missing part here is, I could have easily taken y1 to be the missing part, but I took y2 to be the missing part. There's a missing part which is one of these. X is when y1 plus y2 was given to me. Alright so far? So now what do? Let's think about, now I write the complete log likelihood, and for that let me, if the y's were given to me, when x and y both were given to me, then the log likelihood looks like y1 log 1/2 plus y2 log theta over 4 plus y3 log 1/4 1 minus theta plus y4 log 1/4 1 minus theta plus y5 log whatever that is, theta over 4. So I have all of this. I don't care about that. I don't care about this. I don't care about this. I don't care about that. So when I put it all together, it becomes y2. This I don't care about this quarter either. So y2 plus y5 log theta, y3 plus y4 log 1 minus theta. y1 went away because it didn't have a number that depended on theta. So you end up getting that expression. Now what is the estimate of theta from there? Just as an exercise, what is the optimum value of theta that comes out from here? If I knew everything, what will be the value, what is the optimum value of theta? Remember, this one looks like C log some probability distribution, C2 log some other probability distribution. So what will be the value of theta? So what's that? Exactly. So, but where did it go? It will be y2 plus y5 divided by y2 plus y3 plus y4 plus y5. Yes? Question? Good? Alright. What is the conditional value of y given x and theta? What is the conditional value of y given x and theta? That is the probability that of distribution of y2 given y1 plus y2 and the current value of theta. Remember, y2 is missing, x is equal to y1 plus y2. So this conditional distribution just becomes that if I know the value of x, what is the distribution for y? It turns out that it's binomial with y1 plus y2 with this probability. What is this probability? The probability of y2 divided by the total probabilities. The probability of y2 is theta k over 4. The total probability of y1 and y2 is just 1/2 plus theta k over 4. What is the expected value of y2? It's just y1 plus y2 times this probability. Because it's binomial distribution, the expected value of y2 given the information is nothing but the total number of coin tosses times the probability of a given coin toss. That's that quantity. So now I construct the complete log likelihood, which is this. Take the expectation of y2, everything else is already known. So y2 I don't know what that is, y5, y3, y4, y5 are known, so I take the expectation of that. And now the parameter estimation is pretty clear. This expectation is that quantity, so if I want to iterate, it becomes the maximum of that. And earlier it was simply y2 over here, but y2 is not known, so it's going to be y1 plus y2 pk. That's the expected value of y2, and the other quantities. So here you again have an expression of that form, and therefore the algorithm simply says that it's taking this quantity dividing by the sum and iterate it. Done. That's how it solves that quantity. So let me just go and show you what happens there. Give you a feel for. So here, this is the missing data problem. What did I create? Okay, so theta 0 was 0.25. So which is basically this, the true value of theta 0, I'm setting as 0.25. I'm creating the probability vector, which is going to be 1/2 theta divided by a fourth, which is 0.25 times theta 0, 0.25 times 1 minus theta 0, 0.25 times 1 minus theta 0, and 0.25 times theta 0. N is number of coin tosses. I took that to be 100. Z again is basically a frozen random variable. It's a multinomial NP. Random variables with, I'm taking the zeroth component, it creates an error. Now, sorry, not creates an error, it creates an array. This np.array puts it into an array. And then what happens over here is we are trying to append, we took Z0 and Z1, the first two components, and everything else. So let me run this and then I'll show you what that looks like. Here. So you look at Z, that's what it is. These were draws from the 5-dimensional distribution, 48, 6, 52, 16, 8. These are coming from the distributions that are there. So theta was turned out to be what? 0.25. So basically everything that corresponds to theta has low probabilities, 6 and 8. Everything that corresponds to 1 minus theta has high number of observations, that is 16, 22 and 16. The first component adds up 1/2 plus theta over 4, so it has a pretty high quantity over there. If you look at what x looks like, it should be, if we want to compare them, x is going to be just the summation of the first two components and everything else being appended as it is. So that's what my x is, and now I want to revert back to what it is. In this particular thing, I am directly looking at the negative log likelihood. I defined R to be an array which corresponds to 1/2 plus theta over 4, 1 minus theta, 1 minus theta, and theta over 4, which is the quantity that I'm going to try to optimize over. That's the negative likelihood. I put the bounds to be 0, 1, started from the point work 0.5. This function takes theta and x as inputs. So starting from theta 0.5, the rest of the arguments are x. Again, I'm using the same truncated Newton corporation. The number of iterations are given. If the result is a success, write theta direct. If the result is a failure, then say the direct method did not terminate. And theta, oops, no, that is theta EM, we don't want that. This is what the direct method ended up getting, 0.366. That's the data that it generated. Again, this time around, the direct method turned out the real parameter is 0.25. The direct method ended up giving you 0.4. That is what it is. This is the best one that it could. And it did actually terminate with a success. Otherwise, it would have given me an answer saying the direct method did not terminate. So the maximum likelihood estimate was that. Now, this time around, I am starting from a random theta. And I'm going to run the EM algorithm. So what is the EM algorithm going to do? Remember what is P. Let me show you on the slides. Where did it go? So here, just to make my life a little bit simpler or your life a little bit more complicated, I made a difference between the P defined here and the P defined in the code. In here, I am taking P to be theta k over 4 divided by the summation. In the code, I'm taking 1/2 divided by the summation. So I'm pretending as if y1 is missing as opposed to y2 being missing. It's symmetrical, but it just makes it a little bit confusing. So this is PT. Which is 1/2 divided by 1/2 plus theta t over 4. Theta t is the current estimate for theta. I create z, the current value of z. How do I create the current value of z? I take all the leftover components. Actually, that's an error. So let me fix that. This should not have been x0, but x1, but x0. So I take everything else of x over here, and z was the complete data, so it should have 5 components. So what I did was I took the first component of x, multiplied it by pt. This is the expected value of the missing value of the first component. 1 minus pt is the value for the second component. I put that over there. So now this becomes my zt. Delta t is basically the difference between the new estimate of my theta minus the old estimate. If the absolute value of delta t is less than a tolerance, you stop. Otherwise, you set theta t is equal to theta t plus delta t. You put them into the estimate and keep going. So if we run this, this is what happens. So the EM likelihood turns out to be 0.2771, and in this case it turns out that this is closer than the direct one, and this is what happens to how the theta evolves over time. So theta list is being there, and now if we run this again, you'll end up getting a slightly different one. I'm hoping that, let me actually change this. Let me start it off from some quantity which is actually annoying far away. So let's say theta t equals 0.9. So now it starts from 0.9 and it still converges pretty much there. Yeah?
How the delta t is getting calculated?
Delta t is just the difference.
Every time you are incrementing the theta t by delta t.
No. First I'm defining it to be a difference here.
So what is that logic?
So the logic behind that is that if you look at z, remember, let me show you this. So if you how should I, so suppose I knew all the values of, if I knew all the values of z, how would I compute theta? I will take y2 plus y5 divided by y1 plus y2 plus y3 plus y5. This is the true value of theta that I would get from there. So what I've done is I've got x, I've created a z, now I have a complete data set and I can compute what theta is going to be. So let's check whether that's correct. So if you do that, so it should have been y2 plus y5 divided by all the values of z. Y2 plus y3 plus y4 plus y5, right? There's no subtracting. Oh no, forget about this for the moment. This is the new value of theta. This should have been the new value of theta, except for the fact that in Python we count from 0 rather than 1, right? What I've said is delta t is the difference of the new value of theta minus the previous value of theta. Why? Because I want to check if the difference is very small, I stop. I get out of the loop. If the difference is not small, then I just add back. Theta t plus delta t becomes my new value of theta. I just keep adding back so that we can calculate it there. Everybody good? Okay. So you end up getting an answer. So the point that I want to make by showing you these things is that this EM is actually a fairly trivial exercise. It's not very complicated, and if you look at these Python notebooks, which by the way, this notebook, does everybody have this notebook? You do. You can download it, right? Perfect. So you can play with it, and after you have the Python notebook set up, you can easily compute it. Here's the example of a different kind of, where did it go? Here's a different log likelihood function. So what I want you to do is to recompute this log likelihood function for the first case. In the first case, we assume complete data. I want you to create a new log likelihood function for the incomplete data and just run it just like this and see whether you end up, what estimate do you end up getting, and then compare it to EM, right? Okay, next story, we're going to do this for Gaussian mixture models, but before that I want to show you what happens in the notes. And here there's going to be some other drama that has to be done. The nice thing about Python is that you can then plot various things and have some very nice pictures show up. And for those of you who want to do data analytics, data visualization is just as important as whatever you compete with it. If you're trying to communicate with data and you give me a matrix, it has no meaning. If you give me a heat map, now suddenly there is meaning. So what's going on over here is that I am generating, basically I created Gaussian mixture. So what I'm doing over here in the plot down there, I'm creating a mixture of 3 Gaussian random variables with probability 0.1, 0.4, 0.5. Remember this mixture model? Alphas were there, which was the probability of each of the classes, alpha 1, alpha 2, alpha 3. The 3 alphas are here, 0.1, 0.4, 0.5. The mean is 0, 0 for the first one, 3, 3 for the second one, 0, 5 for the third one. The covariance matrix is basically 1 times the identity. So the 2 components are independent, and on the diagonal there is 1 sitting. The next one has 2 and the next one has 3. All 3 cases, the 2 axes are independent, they are sitting at 3 different means. All that has been done here is basically I created, this is the question being asked was this multiplication. Ravel is a way to unravel everything. These components here I'm creating x's, which is a linear space from -3 to 6 in steps of 200. Y is -3 to 6 in steps of 200. Mesh grid, this is not zip but mesh grid. What it does is that it creates now a matrix. For every value of x, it will take every value of y and create a matrix. So this is my x and y. Now from over this, I take the z and create a function which just, this is 200 by 200. This is this function computed. It's a bit of an algebra just to figure out what the functions are going over there. Now I'm plotting that distribution, and that distribution looks like this. It has 3 bumps at 3 different places. This is the x and y axis, and these are the probability values. So these are high probability values and these are low probability values. So it's got 3 bumps that you can clearly see because it's a mixture of 3 Gaussians. Later on, what we'll try to do is try to figure out how to, given the data, how do I figure out what the distribution looks like? And at the end, after we learn a whole bunch of things in the process, yes?
See the diagram, I can understand, like on the x-axis and y-axis.
Yes?
So the y-axis looks a little bit bumpy at one place.
Yes?
So that small hump sort of thing.
This one?
Yes. No. Yes.
Here?
Yes.
Oh, it's just that it's basically I haven't allowed it to go all the way far away. That's all.
Okay.
I mean, this distribution should have bumped down, but it didn't allow, the axes were not chosen well enough. So it has still not come down completely. That's all. The ranges of the thing should have been chosen bigger.
And another thing, just I'm curious to know that for the 3 different normal distributions.
Yep.
If you take the orthogonals, and which would mean that basically one of them would be true, other would be false, in the sense that then I'm not taking a mixture model there.
No, mixture model basically says that with some probability it comes from that or that.
So if I take the probabilities for one of them as 1, other 2 as 0.
Yes.
So which means that then I'll be seeing the graph at orthogonal planes and only seeing one normal.
You should. If I put these to be 0, you should get the same thing. Yes. So if you put these alphas to be 1, 0, 0, it will tell me the answer. In fact, I should probably make the function to be a little general and fx y alpha. Then you can try the different alphas and see what it looks like. All right, perfect. Now let's go back to our story and see what's going on with the Gaussian model. We have about 10 minutes before we break for lunch. Hopefully everybody is still okay. And where is my view, which gets you to the full, there we go. We did all of this, we got that. All right, now we want to look at the normal mixture model, which is the story that we are going to build towards. Now, how do I construct this normal mixture model? I am going to remember the model was that for each of the classes can belong to one of m different classes. The probability that a particular data is drawn from a particular class is alpha j. Given the class, the distribution of x is given by a normal distribution with mean mu j and variance sigma j. The notes over here are putting the x as one dimensional. In the code, x is two dimensional. We will see that there is no big difference when we go through the code. So the first thing that I need to do is I observe xi and I compute what is the probability that the yi was equal to j. With em, what you have to do is that this is the guy I observe, that's a guy I don't observe. And if I don't observe yi, I just need to compute the posterior distribution that yi was equal to j given the data point and given the current estimates of the parameters. I already know these values. I will pretend as if I know mu and sigma and I know alpha at the current point. Using all of this information, I want to compute what is the probability that the class was some value j. So this is the probability of j given xi and theta k. The probability of j given xi and theta k is proportional to the joint probability yi is equal to j and xi given theta k. This is a trick that we always play because I don't know the posterior, so I'm going to write a joint and then I'm going to write this joint differently. So what is the probability yi is equal to j times the probability xi given yi is equal to j and theta k. What is this probability? What is the probability that a particular ith data point comes from class j? It's alpha kj. Alpha k is the current estimate for the parameter alpha, and therefore the jth component of that tells me what is the probability that the class was j. But now that I know that the class was j, the distribution of xi is nothing but a normal distribution evaluated at the point xi, and the parameters are mu kj and sigma kj. These are the value, this is the mean for the jth class, that's the standard deviation for the jth class. I'm done. Now I know that. That's a normal distribution. So what is the posterior probability? I take the kth quantity. Remember there is a proportionality over here, so I have to convert this into a probability. So how do I convert it into a probability? Take this component and take the summation over all possible values of L, all possible classes, mu L, sigma L, L summed over L. My bag is creating a problem. Right? So that's the probability. So I now have the posterior probability. I know what the complete data set looks like. Now my life is good. I want to maximize this theta given the current parameters, and remember that expression is nothing but for all the data points I going from 1 through n, the expected value of log of p of xi and yi given theta time conditioned on xi and theta k. If I had all the data, this expectation would disappear and it would just have been log of p of xi yi. Because I don't have this yi data, so I have to take the expectation of that conditioned on the data point and conditioned on the current values. How is this expectation written? This is expectation of the probability that yi is equal to j xi theta k. This is the conditional probability times log of p of xi and j. So instead of yi I'm putting j and I'm taking the probability that yi was equal to j. I split this up into two parts. Again, this is probability of j given theta, probability of xi given j and theta. So I split them up into two pieces. This guy is nothing but the log of a normal distribution at xi, mu j and sigma j, because I know the class, so I know exactly what this is going to be. That guy is log alpha j. This optimization now splits up into two parts, one that involves just log alpha j, another one that involves the mu j's and sigma j's. So you split it up into m plus 1 optimization problems, one involving alpha, the other one involving individual sigma j and mu j. Alright, before we go there, let's think for a moment and return back all the way. And in our situation now, what will be the corresponding terms here? Now where is my chalk? Disappeared somewhere. Hopefully I'll have another chalk. Perfect. Okay. Let's look at alpha hat j. This was I'm going to write it in a different form. I going from 1 through n, the indicator function that yi was equal to j divided by n. This is what that alpha j is. Indicator function basically takes the value 0 or 1 depending upon whether the argument is true or false. So what is the numerator doing? It's just counting the number of data points for which yi was equal to j. That's exactly equal to nj divided by n. Now when I don't know the data points, and in this EM story, what will be my EM estimate of alpha? What do you think would be? I'll give you a hint, the n remains the same. What happens there? How would I change that indicator function? Let's go back to the coin example to get some intuition. In the coin example, what did we do? We said that I'm going to take weighted combinations. If I knew exactly which coin was being used, it will be 0 or 1. If I didn't know which coin was going to be used, then I will give a probability that that coin was there and the probability the other coin was there. So what will be, by that intuition, what should be the right answer here?
Probability of all points belonging to class G.
So so we can't do all points. Let's go one by one, I going from 1 through n. And now what do I put here instead of that indicator function? Probability y equals j given what and what? Given xi and given all the parameters theta k. That will be the analogous statement for this indicator value. How did I come up with this idea? One way to think about what happened here was let's take the expected value of that indicator function. I don't know that indicator function. I only know xi and I know the current parameter. What is the best I can do? I can just take the expectation of that. That's the only thing I can do. I have some information. I can take the expectation of whatever I don't know. And what is this expectation? It's exactly what we just wrote. Summation of I going from 1 through n, the probability of yi equals j given xi and theta k. Exactly that divided by n. That's the EM estimate of alpha. Okay? Now let's try for mu. So my real estate is limited, so I'm going to go on to the other side. So let's write the same expression for mu and see what we can do. So mu hat is written as summation of I in S or I in Sj of xi divided by the summation of I in Sj by nj. This is what the expression over there is. So I'm going to write this in a slightly different form, the summation of I going from 1 through n xi times the indicator function yi equals j. That's exactly that summation. The numerator is nothing but this, right? Because every time yi is equal to j, I'll get a 1, I get counted. Every time yi is not equal to j, it just drops off. Divided by nj is nothing but the summation of I going from 1 through n, indicator function yi equals j. Exactly the same thing. Okay. Now what should be my mu according to my EM algorithm? What should I be doing? Every time I see an indicator function of something that I don't know, I take its expectation. Nothing else. So this will become the summation of I going from 1 through n, xi, the expected value of the indicator function of y equals j given xi and theta k. Given all the information that I have, I take the expectation divided by summation of I going from 1 through n, xi, or not xi, expectation of the indicator function yi equals j given xi and theta k. I don't know. Whatever I don't know, I just take the expectation of it with respect to the information that I have. And similarly, sigma j will turn out to be exact, sigma j will be a similar story. So let's go back and see whether this happens, and then we will break, and then we will look at the story with EM there. Let's go all the way back where we were. Okay, so that's where we were. We split it up into m plus 1 optimization problems, one involving alpha, m problems involving individual sigma j and mu j. So if you look at the optimization for alpha, you have summation of j going from 1 through m, summation of I going from 1 through n, probability of j given xi and theta k log alpha j. Remember, this now looks like alpha hat j log alpha j. So if you call this alpha hat j, this is exactly the same thing that we were doing, some coefficient times log alpha j. And how do I get the optimization problem for that? You end up writing the optimal solution turns out to be alpha hat, which is this, divided by the sum of the alphas. It turns out that the sum of the alphas is exactly equal to n, because if you take this summation over j going from 1 through m, so instead of this summation I, you move the summation j inside. So fix a value of I and theta k and sum over j, this probability. What would that be? Forget about this I for the moment. If you take this probability j given xi and theta k and sum it over j, what will you get? Every data point has to come from some class. So if you sum the probability over all classes for a fixed data point, what will you get? 1. And then you'll sum over I going from 1 through n, you get n. So this summation is nothing but n, which is the denominator over here. And what is the numerator? Is the summation of going from 1 through n, probability yi equals j given xi and theta k, which is exactly that quantity. So it's exactly the same story. What happened over here? Summation of I going from 1 to n, probability of j times xi divided by the summation of j going from 1 through I going from 1 through n, probability of j xi theta. So this is the weighted combination. These are the total weights that correspond to class j. This is the weighted combination of points that correspond to class j. This is exactly the same thing, and I will leave it as an exercise for you to figure it out, that starting from the indicator function formulation, if you take the expectation, you'll get exactly this number. It's not very hard to for sigma j write out what the expectation looks like, and you'll end up getting this story. Okay, so let's stop here.